Okay, we're going to talk about coherence now for 5 minutes, I hope, which is also known as similarity or also known as variance. I'm Heather Beadle. I run the AASPI group at the University of Oklahoma. So coherence is one of my favorite seismic attributes. All we're doing in it, even though I'm going to throw out a couple of big words in a second, all we're doing is we're comparing one wiggle trace to its neighbors in different ways and using different ways to calculate how similar that one wiggle trace is to the ones near it. So there's different measures of similarity you may come across, from cross-correlation to eigenstructure to the semblance. And I'm going to start off by just showing you why you should use coherence. So this is one of the first applications of coherence. This is in the Gulf of Mexico. What we're looking at now, though, is a time slice through seismic data. And there's a bunch of faults in here, and I'm going to pause for like half a second so you could try to pick out some of the faults. Okay, Okay, but if we had run coherence, we would have very quickly been able to image all of these faults in this region. You can also see the dark salt dome down at the bottom, and even this really awesome kind of shadow ghosting of a bird's foot delta. So coherence can help you with structure and stratigraphy, probably why it's one of my favorite attributes. In order to calculate coherence, or similarity as we refer to it most of the time in our AASPI software, you need your inline and your crossline dip and your seismic attribute, or your seismic amplitude. So one of the things is a lot of algorithms don't account for dip, and we find here at the university that if you can include dip in your calculation, you're moving along structure better, so you're going to get a much more cleaner similarity or coherence volume as an output. And with Similarity 3D, there's a whole bunch of different products you can look at. And so in this video, I'm going to just try to quickly introduce you to them. And I have some longer videos on the AASPI website where you can get a little bit more detail. But this is kind of like, just trying to show you stuff quickly to get you as excited about coherence as I am. So the importance of computing coherence along structural dip is, wait, I kind of got ahead of myself in my animations, is, if you calculate it along a time slice like shown in this pink area, you won't necessarily be comparing what we would geologically think is related. We'd be comparing along these yellow arrows. If you calculate your coherence along dip, you're going to end up with a much stronger coherence as a result, because you're comparing what's geologically similar. So if we look at this example from Chopra and Marfort's textbook, on the left-hand side, we have coherence computed along a time slice, and so you're getting some of that structural leakage coming through. But if you calculate coherence along structure, like we're seeing on the right-hand side with the pink arrows, you can see those faults are much easier and more confident for you as an interpreter to interpret. Okay. So of course, there's things you should always keep in mind. You've got to have clean data. You may want to use different filters. So lately, our filter of choice the last couple of years is the Kuwahara filter. And also the window size you choose is really important. So are you looking at a 5 millisecond window, a 10 millisecond window? Are you comparing it to the three, like a radius of 3 wiggle traces or 10 wiggle traces? Are you using your broadband data or your multispectral coherence? So you're just looking at certain frequency spectrum of your broadband data. So all of those will give you different results, and depending on why you're using coherence, what you're trying to see, you should kind of consider all 4 of these factors. Okay. So the eigenstructure estimate of coherence is where you first calculate the energy of your input traces, and then you calculate the seismic waveform that best fits the data within that analysis window, kind of shown here. After that, you kind of replace each trace by the scaled version of the waveform and calculate the energy. And then you create your coherence by taking the energy of the coherent component divided by the energy of the input traces. And so if you have the exact same waveform but a different amplitude, the coherence is going to be 1. And so that's really important to remember for eigenstructure estimates of coherence. You can have the same waveform but a different amplitude and still have a strong coherence. Some of the other outputs you may look at are total energy, coherent energy. So in this case, the coherent energy looks very similar to the total energy. We've got all the math up on our website, just so you know. And then here's energy ratio, similarity, on the broadband. Here we're co-rendering coherent energy with the coherence. So we've kind of got an overlying grayscale, which isn't great because we're using two different color bars with gray in it. So if we choose the right color bar, which in this case is one with rainbow colors, it looks much cleaner. So with Semblance estimate of coherence, it's very similar where you get the average wavelet of the analysis window that you're looking at. You estimate all of those coherent traces by their average and calculate the total energy. But then what you do is you look at the energy of the average traces over the average energy of input traces. And so the key thing to remember here is that to have a high coherence of 1, you need to have an identical waveform and amplitude. Okay, so in this case, amplitude variations do matter a lot more. Again, we've got the math in much detail up on our website, but some of the outputs you can get from this are the outer product similarity. Here's an example of it where you can see the higher similarity is white, so those features are very similar to each other. Those wiggle traces are very similar to each other. And here's Sobel filter similarity is another one that's really nice to calculate too. So I was trying to do this really quickly, but I have the longer video up on the website. So the important thing to do is coherence is a great tool. I use it for stratigraphy, structure. I use it for QCing my data volumes. I find that you can spend just 10 minutes calculating it and really evaluate your large data sets much more rapidly. So it's great for QC. It's good for faults, for fractures, and one of the most important things is you want to make sure that the algorithm you're using is always being calculated along dip. Thanks.